Now, one symmetric function that arises frequently is the absolute value function. So it's a friendly reminder that that absolute value measures the distance on a number line away from zero. We also call zero the origin. And remember that distance is always positive. If I'm 5 miles from home, I don't say I'm negative 5 miles from home, right? Distance is always positive. So for example, the absolute value of 7 is 7, because if I go to 7, it is 1, 2, 3, 4, 5, 6, 7 away from the origin. And the absolute value of negative 3 is 3, because if I go to negative 3, it is 1, 2, 3 away from the origin. So when I graph this absolute value function, right, we can also define this as negative x as long as x is less than 0, right? We've got a slope of negative 1, and positive x as long as x is greater than 0. We see that its domain is all real numbers, and its range is just from 0, and 0 is included, that's why we have a bracket, all the way up to positive infinity. So let's find the range of an absolute value function. So let us look at the example 2 times the absolute value of x minus 3 plus 4. So the domain is always going to be negative infinity to infinity, since x minus 3 is greater than or equal to 0 for all in domain. And the lowest value that x minus 3 can have is 0. And when that happens, I get y equals 4. So then y is the lowest value in the range of f of x. So our range is when y is greater than or equal to 4. Okay? So I know that my domain is always going to be from negative infinity to positive infinity. And then what shifts is my range. And we're going to talk about this more in section 1.4. But as you can see, this graph was shifted up 4, right? Its y value starts up here, not on the origin, not on the x-axis. And the same thing is going to be true for here. So let's figure out what the lowest value is. So when x is 0, which is the lowest value of x, I get that 0 plus 2, 0 minus 4 is negative 4. So when x is 0, y is negative 4. So my domain is y as long as y is greater than or equal to negative 4. And this would be a great thing to graph, so you can make sure that you're able to visualize these and see if indeed we did get the domain and the range right. So for f of x equals negative x plus 3, because it's got this negative symbol in front, the graph has been flipped. Okay? So we've flipped the graph, so now our graph is going to be opening downward, but it's also been shifted up 3. Whoops. So here is our graph. So in this case, my domain goes from negative infinity to positive infinity, but our range goes from negative infinity all the way up to 3. That negative symbol flipped my graph over, and this shifted my graph up 4. Now, why am I talking about absolute value functions? Well, I'm talking about absolute value function because they're an example of a piecewise function. Okay? That's a function that has different equations over intervals in our domain. So in the function above, I have negative x defined as long as x is less than 0. So that's the interval from negative infinity to 0. And I have my function defined as x as long as x is greater than or equal to 0. Well, that's the interval close bracket 0 to positive infinity. Okay? And when we union, which means we take together these two intervals, we combine them, we get the entire domain of our function, which is from negative infinity to positive infinity. So I want us to practice graphing quite a few of these because this is something that more students get caught on than you'd think. So why don't we go ahead and graph this. So I have, as long as x is greater than or equal to 3, 4x plus 1. So where is x greater than or equal to 3? So let's divide my domain. So here's where x equals 3. So as long as my graph is x is greater than or equal to 3, I have the function 4x plus 1 is defined. And then as long as x is less than 3, I have negative x squared defined. So we need to go ahead and graph these functions, okay? If you don't know already what these graphs look like, you can always pick some values. So for 4x plus 1, I need to know my x value when x is 4, 5, and 6. Well, I really only need 2 points to graph a line, but let's do 4 and 5. So when x is 4, I have 4 times 4 plus 1, which is 15. When x is 5, I have 4 times 5 plus 1, which is 21. Okay, so my graph's like way up here, right? Because this is 7. So my graph's going to be all the way like up here with a slope of 4. And my endpoint's included, so my value for 3 is included. You know, I'm going to try and graph this a little bit better, okay? Maybe we'll scale our graph. How about that? So let's use a scale of, how about 4? So I have 4, 8, 12, 16, 20, 24, 28. Okay, so when x is 4, y is 15. That looks like about 15, right? When x is 5, y is 21. Okay. When x is 3, y would be 4 times 3 plus 1, which is 13. So right about here. And this is supposed to look like a straight line. So I'm going to graph that. Okay. Now, my endpoint is included. So I put a solid dot. Now I have the graph when x is less than 3. This is a parabola. 1, 2. Okay, so when x is 0, y is 0. When x is 1, y is negative 1. When x is 2, y is negative 4. And as you can see, this one's kind of been like stretched out because we changed our scale. Now, when my parabola crosses this boundary, this parabola isn't defined when x is less than 3. So I'm going to leave that as an open dot. So here's the graph of our first piecewise function. Remember, this is a function because it does pass the vertical line